Okay, kids, new video for 2017. Let's see how long I try to use this in the future. Okay, this is about dilations. We've had a bunch of isometry so far for our transformations in geometry, and this is the first one, and really the only one we're going to talk about, that does not preserve distance. When things change under a dilation, they actually get closer together or farther apart, and distance is not preserved. Sometimes it's called a scaling, sometimes it's called a similarity transformation, and it's going to enlarge or reduce a figure. That's not how we tell it to operate. Like, those aren't the instructions we give it, but that's going to be the effect of it, and that's what's so important about it, and that's why it gets this term and this kind of description. Okay, so the details about a dilation before we perform it, and by details I mean, for reflections we had a line, and for rotations we had a center and a magnitude, and for translations we had a vector. For dilations we have a center, just like for rotations, and this time we have a scale factor, which kind of sounds like a magnitude. But a scale factor is like a multiplier that's going to act as a amount that we're going to enlarge or reduce, an amount that we're going to zoom in or zoom out. But it's very much a multiplication kind of feeling here. So the dilation D, and D is the letter we use for the capital letter for the act of dilating, like the curly R for rotation. And then the little subscripts down here are O for the center point and K for the scale factor. And we use scale factor in the similarity chapter, and that's not an accident. We use the same. It feels like the K we used back in that unit. So this is how it works. It takes any point. Well, first of all, it takes the point O and it doesn't do anything with it, just like rotations. If K is a number that's greater than 0, this is kind of a cumbersome description. P prime lies on the ray that connects O to P. Now, P is the preimage point. So we start by drawing the ray from O to preimage, and we just kind of expand or contract. We measure this distance from O to P, and we multiply that distance by K, and where that ends up is where we put P prime, that distance away from O. If K is negative, we do the same process, but we go the other direction down the line. It's easier to just do this and show you how it works rather than read this again. And we can call it an expansion if K is bigger than 1, and a contraction if it's between 0 and 1. Okay. Let's just do some. Okay, so find the image of triangle ABC under the dilation D, center 0, scale factor 2. I'm going to need my ruler. Boom. Okay, I wish it was longer. Can I make it longer? Can I just... Oh, I can. Sweet. Just do that with your ruler. Okay. So we measure from O. We always put the 0 of the ruler on O. It's kind of like when we were doing rotations. We always put the center of the protractor on the center of the rotation. Okay, so we measure from O to B. B is the preimage point, and from O to B on mine here, it's like 75 millimeters. So I'm multiplying that by 2. Leave the ruler exactly where it is. Let me write down what I'm doing here so you can see this later. O to B, right now, that distance is 75. So that tells me that the distance from O to B prime ought to be 2 times 75. That's all you do. And that's 150. Now, realize that's from O to B prime. So I leave the ruler exactly where it is, and we look up here at 150. Can I do this easily? It's hard to write on this perfectly. And right around there, you can barely see it. That's where we put B prime. And the fact that I left the ruler right there the whole time ensures all this stuff we were saying here about ray, OP, and lying on the same ray and all that stuff. That just means leave the ruler where it is when you start making this number line to go from here at 0 to B, go the same distance, just keep going that same direction. Okay, so let's do a different point, and then it'll start to look interesting. All right, so put the 0 at the ruler on O again. I gotta do this to move it. Wrong way. Sorry. Oh, that's annoying. What happens if I do this? I want to move my ruler a different direction. Okay, there it works. All right, so move this up here. This is frustrating. Electronic rulers are hard to move. Okay, so there we go. So I want to measure from O to A. That's about as good as I can get. Measure from O to A, it's about 88. So O to A prime is going to be like 2 times 88, which is 176 or so. So right around here, I'm going to have another point. I'm going to call that A prime. And then O to C is going to be like here. That's about as much as I want to frustratingly move that. O to C is like 13 point something, so I'm going to go to like 26 point more than that, and it's something like, like there. So right around that point is where I'm going to say C prime. Now look what happens to this picture when I do all that. So I'm going to connect this. I'm going to cheat kind of and use my straight line tool. So all those points got thrown essentially twice as far away from point O as they once were. Can I just get that out of the way? So notice this distance from O to A just got doubled, and here we go, and O to C and doubled, there we go, and O to B doubled, there we go. The resulting triangle is twice as big as it used to be over here, and that's all related to this fact that the scale factor was 2. I didn't create this by trying to make a triangle that was twice as big. All I did was expand from the center of the universe here. Everything just went twice as far away as it was along their respective lines, and I ended up with something that was twice as big. Here we go. Oh, they want pre-image. Okay, so this is the primed version. I want, if this is the primed version, where was the original if this is the twice as far away version? Well, if this is the twice as far away version, then the original had to be closer. So this O to R prime, I'll write this over here. This O to R prime, that was double the distance from O to R. So in other words, O to R is half the distance from O to R prime. So O to R prime is about 70, so about here at 35. Can I easily do that? I don't know if I got that or not. Yeah. So right around here is R, right around, oh, can I do this quickly? I know it's fun to watch someone else move around an electronic ruler. Okay, 0 to, it's about the same distance there. So this is T prime, and I'm just going to eyeball it. S prime's right there. And so the new triangle, again, should look, and this is called the similarity transformation. Yeah, it's in every way similar to the original. It's got the same angles, and all the sides happen to be half as big. But what's also important about this dilation is not only that we end up with this triangle that's that size, but where it's located. You notice S prime O, it's collinear. R prime O is collinear, etc. So location is also a big factor here. Okay, find the coordinates. If we're doing dilations on coordinates, look what happens. All we do is multiply coordinates if the center is 0, 0. So this is kind of a big deal. If it's centered at the origin, what's nice about that is dilation by coordinates just simply means multiply the coordinates by the scale factor. So 0.23 is going to go to 0.46 with a scale factor 2. Points like M are going to go, they end up just going, what happens in that case is they'll just go twice as far away along the same kind of path from 0, 0. All right, so let's do this. Find the image of, I probably don't need this anymore. Find the image of ABC under this dilation of 0, -half. Okay, this is fun. So right now, the coordinates of A are at -2, -4. So if I multiply that by half, -half, that's going to turn into +1, +2 for A prime. So +1, +2. It goes the opposite direction. C is at 0, 4, so I'm going to go to 0, -2. And B is at -4, -2, so I'm going to go 2 this way and 1 this way. It's going to go that way. So what we end up with is actually going to be similar to the original, but watch what it looks like. That is actually similar to the original. It's got all the same angles and everything, but you'll notice it's kind of flipped over. It's a dilation, and it's also got a half-turn rotation involved in it too. That's what happens whenever you throw things with a negative scale factor. And so what it's doing, it's just kind of going backwards. So remember, the 0 in the number line is always here at the point 0. So when we measure to A, it's like I was taking a ruler and measuring that way. Well, negative along that number line, if this is positive however long it is, negative however long that is should be this way. And this is -half as far, which is why all these points are closer than they originally were that way. And it's negative, so they're the opposite direction. We already talked about this. Going the opposite direction around O is like one of those algebraic reflections in the origin, so everything kind of goes backwards from the original, from the 0, 0 point, the same amount if it's a half, if it's a half turn. Well, this is a half turn, but it's also got a dilation associated with it. Okay, so find the image of this now. If we take this and that, so this one I just drew, I'm gonna change colors, and we dilate that -4. So this is at 1, 2. I have to go -4, -8. It's way down here. Double prime. C was 2 downwards, so now it has to go 8 upwards, so it's up here somewhere. and b is 2 and 1, so I got to go back 4 and down. Oh, that's like where I came from, really? Oh, no. It's times 4. So 2 and 1, so I got to go 8 and 4. Yes, it's right here. Again, this should all be similar. I think my color is still going to be blue here, but this is the answer to part B. And hey, guess what? We've half turned again, so we're kind of facing the same direction as the original. Shouldn't surprise you too much. Find the scale factor that took this purple one to this final huge one. Well, right now, from here to here is so far. How much farther is it this way? Well, it's exactly twice as far. Well, if you look at this, -1/2 times -4 is exactly 2. So this would be scale factor is 2. You can tell by looking here, from O to C is that far. From O to C double prime is twice as far. Same thing with B and same thing with A. That was fun. Yes, you can multiply scale factors. If the dilation 0, -3 or O, -3 takes R26 to R prime, well then R here should be, there's 2 ways to do this. This would take us here, correct? We'll just multiply all those coordinates. Find the distance from O to R prime. From O, which is the origin, 0, 0 to here. 2 ways to do this. We could just find the distance from 0, 0 to this point, which isn't too bad. That would be this. Whatever that is. The other way, that's funny, or the other way we could do it is we know the distance from O to R prime should be 3 times the distance from O to R, which is the distance from 0 to 2, 6. This is almost easier to do in my head. And I know I'm going to have the square root's going to be reduced already nicely. That's 36 plus 4, which reduces some more. But I'm sure this will be equivalent to that. I'm trying to save you some time here. Okay, then here's where I get into some stuff that I wanted to make sure we picked up from last time. Let me just fill this out and have you look at it. Okay, so there's the first 5. I'll do this last one while I talk through it. Okay, so for all of these, what we're looking for is whether this happens. Does f of -x equal the same thing as f of x? And this is from the first part of the lesson. Or does f of -x equal the opposite of the regular old f of x? If this is true, then we say it's even. If this is true, we say it's odd. So we always start out with this f of -x thing. And then you try to simplify it and see if you can get it to turn into one of these things. So keep in mind what that original thing was and think about what it would be if the whole thing were negative. So, okay, so I put in -x for all the x's, which is this is -x. Whoops, -x minus 3 squared. And this might help to think of this, just so we have this as a placeholder. It might be kind of nice to know that this is, that this is minus 6x plus 9, just in case we need to know that. And then, so the negative f, so this version of that, negative f of x would be -x squared plus 6x minus 9. Because what is this? I got to see, I have to kind of reconcile this and see if it turns into that. -x squared, that part would actually be x squared. This part, you know what would be easier? Let's just say this. This is the same thing as if I negative all of this and square it. Wouldn't that be the same as x? Well, that's dangerous, I guess, too. All right, so this middle part would be -x times -3 times 2, which would be positive 6x, and then -3 squared is plus 9. So at the end, we get this. We don't get this. We don't get the negative version of this, so this one turns out to be neither also. Okay, we didn't get to anything like the next couple pages. If xy is on the graph, what is also on the graph? Well, on this kind of thing, if we have some point xy like this, I also know this point over here is on the graph, so same y with the opposite of that x. If it's an odd function, so these are even. This is even. This, of course, is odd. This is just kind of strange. It's neither, but it's not the only way to be neither. Right? This has some kind of symmetry, but it's not even or odd. Okay, if this is on the graph, so if some point xy is here, I also know that there's kind of a corresponding point down here. Xy and negative y are both on the same graph. It's odd. Here, if xy is on the graph, I have the same the same x with the opposite y. That's actually not very useful for anything. This last page is kind of a geometry exercise. I don't have much time, so I will just fill it out first for you. Okay, so for basically all of these, I just completed the transformation in geometry that they asked me to do. So x-axis reflection, y-axis reflection, origin reflection, of course, means a half turn around the 0, 0 point. And that's all we did. Okay. Oh wait, last questions. Function, odd, even, or neither. Okay, now those are filled in. If it's not even a function, it feels strange to say whether it's either odd, even, or neither, because it's not even a function. Okay, enjoy. See you in class.